The topic of this lecture will be carbocation rearrangements. A carbocation rearrangement is a structural change of a carbocation to create a more stable ion. Remember that, because the carbocation is electron deficient, a more substituted carbocation is a more stable carbocation. Typically, we see one of two types of rearrangements occur in carbocations. Sometimes we see a hydride shift. Remember that hydride is a proton with 2 electrons. A hydrogen with 2 electrons will have a -1 formal charge. The other type of rearrangement we see is called an alkyl shift. This involves the movement of a carbon atom and its attached atoms. We'll now look at these types of rearrangements in more detail. The following reaction involves a hydride shift. This substrate undergoes substitution to give 2 different products. We get this substitution product and this substitution product. We will call these products A and B. Product A is formed through a typical substitution reaction. Take a moment now, pause the video, and see if you can draw the mechanism to form product A. Product A is formed through the normal SN1 mechanism. In the first step, the leaving group leaves, forming the carbocation. In step 2, the nucleophile, which is methanol in this case, attacks the carbocation, forming the substitution product. In the final step, this ether is deprotonated to give the neutral product A. The mechanism to form product B is a little more complicated. Step 1 is the same, where the leaving group leaves to form the carbocation. It is the second step where things change. The next step involves a hydride shift. We will redraw this carbocation intermediate so that we can see the hydrogen that's moving in the next step. It is the hydride on the carbon adjacent to the carbocation that will move. Remember that it's a hydride shift, so it's the proton plus its 2 bonding electrons, which make up a hydride. Accordingly, we draw the arrow from the bond to hydrogen to the location of the shift, which is the carbocation. This is where the hydride shift occurs. Because the hydrogen is taking its bonding electrons, it is leaving behind an electron-deficient center, a carbocation. The carbocation has effectively moved then to the adjacent carbon where the hydride started. The driving force for the hydride shift in this case is going from a secondary carbocation to a tertiary carbocation. Again, remember that more substituted carbocations are more stable. Once we've formed the tertiary carbocation through the hydride shift, the rest of the mechanism looks the same as for the formation of product A, except now the carbocation is at the tertiary center, giving us the ether product at the tertiary center. Next, the methanol nucleophile attacks the carbocation center, giving us the protonated ether product. And the final step is deprotonation to give us the neutral ether product B. Now we will look at an example of an alkyl shift. An alkyl shift involves the shift of an alkyl group. This can be as small as a methyl, but sometimes larger alkyl groups shift as well. Let's look at the following example. This molecule undergoes an alkyl shift when undergoing an SN1 reaction with methanol. The product that we get from this reaction looks like this. Clearly, this did not occur from a simple substitution of the bromine with the methanol. This is due to the alkyl shift. Let's look at the mechanism. Remember that the first step of an SN1 mechanism involves the leaving group leaving. However, if the leaving group leaves, we will be left with a primary carbocation. However, we know that primary carbocations are very unstable and basically do not form. What happens instead is that there is a concurrent alkyl shift with the loss of the leaving group. The alkyl shift that occurs is the movement of the methyl from the quaternary carbon to the primary carbon that is attached to the leaving group. Just like with a hydride shift, the methyl group moves, taking its bonding electrons with it. The product of this step looks like this. The carbocation that is formed is tertiary rather than primary, which is considerably more stable, forms a lot faster, and is the major product of this step. The mechanism then proceeds as a normal SN1 reaction. The next step will be attack of the nucleophile on the carbocation to give us the protonated ether product. The final step is deprotonation to give us the neutral ether product. Hydrogen and alkyls occur in reactions that involve a carbocation where such a rearrangement can form a more stable carbocation. Typically, this involves a primary carbocation being rearranged to form a tertiary carbocation or a resonance-stabilized carbocation. Occasionally, we will see a secondary carbocation rearrange, but this only occurs in special cases. You should consider that a rearrangement could occur if loss of the leaving group would form a primary carbocation. Use this strategy when you're asked to predict the products of an SN1 reaction. If you're asked to predict the mechanism for formation of a particular product, you should consider that a rearrangement might occur if substitution appears to have occurred at a carbon that did not contain the leaving group. These strategies should help you identify problems that contain some sort of hydride or alkyl shift.